Okay, so good morning, everyone. So let's start our seminar. Okay, today we are very excited to have Dr. Shiwen Mao here. Dr. Shiwen Mao is a professor and eminent scholar and director of the Wireless Engineering Research and Education Center at Auburn University. So his research interests include the wireless network, multimedia communication, and smart grids. So he's an HOE fellow and also the editor-in-chief of HOE Translation on Cognitive Communication and Network. So Dr. Mao has received numerous awards, like include the Outstanding Research Award, Faculty Achievement Award, Distinguished Technical Achievement Award, and a lot of Best Paper Award. So, okay, now I pass the time to Dr. Mao. Let's welcome him to give us the talk.
Thanks for the kind introduction. Good morning. It's really a great pleasure and a great honor to visit your beautiful campus. Actually, I was here in the summer attending a conference Professor Shi organized here. So I'm really glad to come again and to meet old friends and make new friends. Okay. So I'm from Auburn. So this is a college town, like 50, 60,000 people, very close in Alabama, but we are on the border of Alabama and Georgia. So very close, 90 minutes to Atlanta. So we always go to Atlanta for fun, for nice food and travel. Yeah. So this is a joint work with my current student, Ziqi, and two former students. Basically, they should have all the credits. They did all the work. And yeah, the topic is AIGC. So that is a kind of hot topic. But we want to apply it to wireless data, to wireless problems, wireless communications problems, sensing problems. Okay. So this is an outline. First, we talk a little bit about the motivation. So the challenge in collecting, creating wireless data sets. Okay. So probably you have seen this before. So we talked a lot about these generations of cellular communications. So actually, I was in college at this time, and I was in graduate school during this middle of the second generation. Yeah, actually, I think Professor Xia, probably you have been contributing to all of this. Yeah, so now we are in sixth generation. So then the question is why we call it a generation? Well, what is a generation? If you look at the dictionary, so you need to have some like a new fundamentally disruptive technology that has been used for most of the devices. Okay, so then you can call it a generation. But if you look at the earlier generations, it is always like that. So 2G, then you immediately think of GSM, 3G, WCDMA, then 4G LTE. Then now the question is about the 5G and 6G. So why we call it a 5G, fifth generation? Because there's so many different technologies, people call it 5G. Then making it very difficult to define what is 5G. You talk to people, different people give you their own vision. What is 5G, fifth generation? And they have to, the standardization people, they have to define three very different kind of application scenarios. And they have to define very different kind of performance metrics. Okay. But later on, when we are like, we're in a middle way, 5G is being rolled out in many countries. So people realize that maybe intelligence, machine learning AI is the definitive like a feature for the next generation. So if you look at I was working on cognitive radio more than about 20 years ago when I was a postdoc at Virginia Tech. So basically, if you look at this cognitive loop, so basically you have a spectrum sensing, you sense the radio environment, then there's a cognitive engine that makes decision. Okay, so what to do. sorry, let me go to my. So then the decision will be executed by a software-defined unit. So this is cognitive loop. So if you look at this, this is very similar to what we have talk about now, machine learning AI systems, right? So then many people are working, including myself. We start to work on applying machine learning to address wireless problems. And one trend we observe is that the networks, the models are getting deeper and deeper. Okay, so these are the winners of this ImageNet competition. So these numbers are the accuracy, error rate. First 28%, then it's very shallow models. Then eventually 2015, then people are using hundreds of layers, very deep models, and the accuracy becomes so high, they stop organizing such competitions. It's always more accurate than human users. Then, yeah. So if you look at the other, more recently, there's this exponentially growth in the model size. So this charts this number of parameters, and this is the time axis. So basically, it's plotted in the log scale. So you see a linear here. That means there's an exponentially in growth in the size of models. And similarly, is here. So in the past, we talk about Moore's law. So basically, the integrated circuits, the size will double every 18 months. But now we have reached the physical limit. So people say Moore's law is dead, but for machine learning model, probably there's a new Moore's law. Yeah, you see this in the log scale, but this linear here, exponential growth in the model size. And then what's the implication of this kind of growth? So if you so probably you have seen this kind of curve before. It's the sample complexity analysis. So it answers question: how much data you need to train your model? So this is the performance, accuracy, or loss, error. Then this is how much data in log scale. So usually you want to enter this power region so that you can get a very fast reduction in your error. Okay, but beyond this point, more data will not be helpful. So, but there's a log exponential relationship here. Similarly, for this image recognition results, you can regress this linear relationship between this data and the loss. And then this is the linear relationship between data size and the model size. Yeah. So for image processing or recognition or text like based applications, data is easy to obtain. You can get tons of data from the internet, whatever images. Okay, but for wireless data, then this will be a big challenge here. Why? Because if you look at this simple example, so the received signal, okay, from transmitter 1, there's only one single pass. The received signal from transmitter 2 is the sum of these two, direct pass and the reflected pass. So if there's the obstacle or the environment change, then these two signals can be destructive or constructive. So when there's a small change in the radio environment, then you get a very different results. Okay, and then we have very different devices, wireless devices, different channels, different bands, different protocols, device drivers, so different hardware. So they'll give you very different kind of data sets. Okay, so like here, these are the range profile we collected from these mmWave radar systems. This is the RFID, the phase angle in the RFID response. And these are the channel state information from Wi-Fi. So they are very different. They have different meanings, different formats. So then there's a lot of diversity here, okay, and sensitivity. So also wireless data is very costly to collect. So you need to, for example, Professor Ted Rappaport, he was the very earlier researcher on collecting millimeter wave data. So that lay out the foundation for 5G. So he was lucky to get like a $300,000 equipment, channel sounding equipment from Samsung, so he can hire students to do the optimization. But the device is very expensive and it's very labor intensive. So like my students collecting this human pulse recognition data, he needs to perform between this before this wireless transceiver some activities for 2 hours. So if you are targeting 10 different applications, that's 20 hours. Then you need to consider different environment and the lab environment, apartment, a corridor. Or you need to consider different subjects, a female, male students, or tall guy, short guy. Then that will increase your effort considerably. Okay, now this is an example. We collect data for indoor fingerprinting localization. So we need to collect data at each of these points for like 400 packets transmitted, received at each of these points. So that is takes a lot of time. Okay, and this data expands spectrum, time, space, different signal noise ratio, different protocols, different hardware. So, and once you collect the data set, then it will be very difficult to generalize. So suppose you collect data set in this room, then you want to use your trainer model using that data set, but you want to use the trainer model in your apartment, then probably you get a very different results. Okay, it's very difficult to generalize. So I think I can skip, but the success of machine learning has been triggered by this ImageNet competition. But for ARF data, wireless data, there are a lot of differences. It's very difficult to replicate the success of ImageNet. Okay, so then what shall we do? So from statistics and then such problems have been well studied previously. So you can do like a data imputation. So that means suppose you have an outlier, you have a missing samples. Okay, then you figure out some way to estimate their values. Like you can use the average of all the neighboring examples to replace this outlier. Then you can have imputed data. Or data augmentation is that we try to increase the size of the data set. So suppose you want a lot of pictures of tigers, but you only have a few, then you can change the contrast, you can clip it, you can change the add some noises to it, you can turn it around. Then this way you can generate more images of tigers you can use to train your model. Okay, but for so here next slide will show you some examples. So this example is that we put the RFID tags on the joints of the human body. Then he will perform some activities by querying these tags, interrogating these tags. Then we extract the face angle from the tags. Then we can estimate the human activity, okay, human pose. But the change here is that there is some multi-access protocol here. So the antenna or the reader queries this 12 tags. Anytime only one tag can return a response. Okay, so we have 3 antennas to query these guys. So you see three rows. Then we have 12 tags. Then each vertical slice is a time slot. So in each time slot, we're supposed to get 36 samples, but we can only get 1. It's a very sparse data, but somehow we can apply some techniques like a tensor completion or some other techniques. You can estimate those white blocks, those missing samples, then still make it work. Okay, so that is one example. And also you can, for these sparse measurements, then you can apply some deep Gaussian process to regress a continuous radio map. Okay, so out of these sparse measurements, then you can do a lot of things with the radio map. So this is the early trial attempt we made to use GAN generative GAN, okay. You use this GAN to synthesize wireless data. So this is a very popular data set that is simulated from using a device called USRP. So for different modulation techniques, okay, then at 20 different signal noise ratios. So, but for each category, each modulation and the SNR level, there's only 1,000 samples. So if you use this to train your deep learning model, 1,000 samples seems not enough, right? So we somehow use a conditional GAN to from random noise, we can synthesize this data to increase it from like 1,000 to 5,000. You can, once the model is trained, you can generate as many models as you like. Then they look very similar, and they can be used to train the model to improve your model's accuracy. Okay. So the rest of the part I talk about AIGC. So that's more recent topic. So AI generated content. So our target application is this sensing human pose tracking. So it's like suppose you have this is a video, a picture. You have those human bodies. Then you can cut each human body out from the background. Then you can represent each human body with a skeleton. Then this has a lot of use applications. Like you can make movies. You can, once you like the Avatar movie, and you can let the actor, actress to perform the activity, then you extract the skeleton and replace the skeleton with some other any form you like. So my student is working on this piece right now. So you can, this can be used for, it's an important means of human computer interaction. So like probably you have seen this. Apple call this spatial computing. So basically you control, there's a virtual display in a goggle or glass of a keyboard or app. So basically you use a finger drag in the space, then you can control them. Like this guy, he's doing this in the New York subway. Okay. Then
what is he doing there?
I don't know what he's playing, maybe a video game. This is a Vision Pro, is very expensive, so touch screen. Yeah. So this all hinges upon the accurate tracking of your body parts, your gesture, your fingers. Currently, this is done with very high accuracy video cameras. Okay, but we want to see if we can do this using wireless signals. Okay, because wireless sensing is non-obtrusive, so you don't feel being watched all the time. So Wi-Fi is here, we don't feel it. So it's more friendly and privacy friendly. Okay, conserving. So, but the challenge is that for images, we can clip, we can change the contrast, change color, we can rotate. But for wireless signals, it's a cosine wave. It's an EMAG kind of a field. It's propagating in space. Then how do you clip it, rotate it? How do you manipulate it, right? So the trick is that we're doing pose, right? Pose monitoring. So we can manipulate this human pose, okay, as we wish. Then the next step is to translate this human pose, manipulated human pose, into the desired wireless signal. So that's the trick. So to do this, it's like using this ChatGPT. Okay, so you have a user prompt. So basically, you tell the system what kind of activity, how tall this guy is, how long the arm is, things like that. What kind of activity you want, then feed this into a pre-trained model. Then it will give you the desired wireless data. Yeah, then this can be done in two most popular techniques. One is the GAN model. Okay, GAN model. So basically, it has a discriminator, it has a generator. The generator will synthesize from noise. Okay, synthesize a fake sample. Then discriminator will try to distinguish this fake sample and original real sample. So once the model is trained, the discriminator cannot distinguish this X prime and X. Then the generator can be used to generate data. Okay. Then later on, there's a 2020. There's a DDPM model. Okay, denoising diffusion probabilistic model that was published. So the idea is that you have a valid sample. So you keep on adding small noises to the sample. Then you get X1. Then you add more noise, you get X2. Until you destroy this sample into white noise. Okay. Then during this process, we can learn what kind of noise to be generated to destroy it. Then in the reverse direction, so we start from white noise. So we generate those noises, subtract it from this Z, then step by step, we can reconstruct a valid sample. So that's the idea, okay? So this is the system we use for, we call R-GAN. It's a recurrent system, neural network. So to synthesize wireless data. So we still need to collect the like 2 hours or 4 hours real data. Okay, so these are the used to train this generator and discriminator. Okay, so once the generator is trained, then we have this prompt. So what kind of skeleton you want to use, and what kind of activity and some other things you can fit into this generator. Then the generator will synthesize data. Okay, for you. And then this synthetic data can be used to train your downstream models. Okay, then we want to see how effective, how useful the fake data, synthetic data is. Okay, and this generator consists of this autoencoder with RN. Then the discriminator is a CNN model. Okay. So so for this prompt, we want to first generate a skeleton as a prompt input. So this can be generated, simulated using a tool called Blender. It's an open source tool. Okay, then we feed this into the model. We ask the model to synthesize data corresponding to this specific skeleton. So there's one challenge is that so what kind of data you want? So there are two extremes. Two goals, conflicting goals. One goal is you want to have synthetic data that looks similar to real data, right? So, but if you just want the similarity, you can simply copy and paste the real data to multiple copies. Then you get exactly the synthetic. That's exactly the same as the real data. But this does not help because you don't have new information. So the other extreme is that you want the diversity. You want the data to look different from the real data, okay, but in a controlled manner. So we want to introduce enhance diversity of distinct data. So one way is to introduce a small Gaussian noise to the human joints. Initially, it's here, then add a small displacement. It's like when some subject perform activity like waving hand. Some people they have a large extent, some with a small extent. So basically, you can introduce a lot of noises, and then another way is to introduce variations like impose. This is the original one. Then we can make this guy taller. Okay, leg. Make the leg longer, for example, or change the extent of the activity, like you want to wave your arm to a larger extent, or change the camera angle and change the location. So this way we can introduce diversity, okay, into the system, into the data set, okay. Then we implement this using we tried actually 4 different wireless systems. So one is RFID that operates in the 900 megahertz band. We have a millimeter wave radar that is 70 gigahertz, okay, and the Wi-Fi at 2.4 gigahertz and 5 gigahertz. Okay, so 4 different systems. The devices here. So this shows how the training data was collected. Okay, imagine you're doing this for 2 hours to collect enough data to train a model. Okay, yeah. So how does the synthetic data look like? Okay, so we have 4 systems: Wi-Fi 2.4 gigahertz, 5 gigahertz Wi-Fi, RFID, and 900 megahertz, and the mmWave radar 70 gigahertz. So this is the video data. That is the ground truth. So you see the different activities performed. Then we have the ground truth. So this is the synthetic data. So if you compare these two, you can see there's a lot of similarities between the ground truth and the synthetic data. And then we can go one step further. We can use different metrics to assess. You have 2 original data set. You have a synthetic data set. How similar? How to compare? We can define these similarities. So one easy way is to compute this signal noise ratio, but that's not helpful. Pixel by pixel kind of comparison, because you don't want to have identical data sets. You want diversity. Okay, so we can use this structural similarity index. Okay, so the results are given here, and all these this will evaluate the structure and the features of 2 like images. So you have an apple here. You also have an apple there. They are which location they are within the image. You can compare these kind of things. And this RFID score can compare the distribution of those 2 data sets. Okay. And then we also define some like diversity, okay, and multimodality. So this is, we compute the variance within, across all different, 10, 12 types of activities. And this is the variance we computed through a few selected kind of activities. So you can see here this SSIM score. So if it's close to 1, that means exactly identical. Okay, but you can see this 0.8, 0.9 range. So that means that visually the synthetic data looks very similar to your real data. Okay, and then this RFID score distribution. So this corresponding to the 2 ways to introduce noise to the synthetic data. So this is the introduced Gaussian noise. This is, we change the activity a little bit. So, and these are the results for metrics for real. Sufficient real means 2 hours of real data, and limited real means like 17, 18 minutes of real data. So you can see RFID score wise, the GAN model doesn't perform very well, but for diversity and multimodality, they are very similar to the real data. Then the ultimate test of how your fake data, your simulated data, how useful it is to use this data to train a model. You use real data to train a model. You use your synthetic data to train a model. Then compare the performance of these 2 trained models, right? So we consider 2 downstream tasks. One is this 3D pulse tracking. So basically, we have a RFID or Wi-Fi or mmWave data feed into this autoencoder. Then the output will be a human skeleton. Then we compare the error. So originally, your arm should be here, but this predicted skeleton say your arm is here. So the difference is that is the error. Okay. And we tried different kind of data sets. So basically, we can check out these 2. Sufficient real means like nearly 105 minutes of real data collected by my student in front of these wireless transceivers. And then we have an augmented data set. So that is 440 minutes long. It's much longer than this, but it includes like 420 minutes of synthetic data, plus this like 80 minutes of real data. It's a mixed. Okay, then this real data is more like used like fine tuning the system. So then their performance are here. So this shows the these lines are the distribution of error distribution. Okay, so if you look at these 2 lines, one is limited one is sufficient real data, 105 minutes of real data, and the other one is augmented data, this green line. You can see their errors are very similar to each other. Okay, so that means the synthetic data is useful. You can use it to train your model. Okay, that give you a good performance comparable to the performance of a model trained by real data. And then we try to increase the amount of synthetic data from this is like 17 minutes of real data. Then we add more synthetic data to this set. So the curve will move up and to the left. So that means the model trained by such data, augmented data set are becoming more and more accurate. The error is like 3-4 centimeters. Okay. And it worked for RFID, for this 2.4 gigahertz Wi-Fi, 5 gigahertz Wi-Fi, and mmWave. So that is really interesting. Okay, it's not it works across different technologies. Okay. Although these are very different wireless technologies. This is a range profile, 70 gigahertz. This is a phase angle, like 900 megahertz. Okay, very different in their meanings. Okay, and the format. The second downstream task we tried is activity recognition. So we collect this Wi-Fi or RFID, whatever wireless data reflected from human body, and feed this into this CNN model. Then the output will tell you what kind of activity it is. Okay, so this is a classification problem. Previously, the 3D pose problem, that is a regression problem. We regress a continuous move of the video for the human pose. But similarly, we also see these improvements. Okay, in accuracy, classification accuracy, once more synthetic data used. But keep in mind, this synthetic data, once the model is trained, you can get like 300, 200 synthetic data at no cost. You don't need to spend time to work in front of the video transceiver, right? So you just run the trained model for a little bit long time, then you get more data. So this is one advantage actually. It saves a lot of efforts in collecting wireless data sets. Okay, then finally we tried this more recent diffusion model. Okay, as we we talked before. So there's two process. One is forward diffusion. So you have a valid sample. You keep on adding noise to this, okay, until you destroy the sample to noise. Okay. Then in the backward reverse diffusion, we keep on subtracting noise from this Gaussian noise until we get a valid sample. Okay. So then the question is, what kind of noise you want to introduce and you want to subtract from? So basically, that's learned by using a UNet model. Okay. So in the forward diffusion process, we learn what kind of noise we should generate. And this shows an example. So from noise, each time we subtract some noise, then eventually you get an image, right? So this is the example, like starting from noise, we subtract some noise from it every step, then eventually we get a RFID data. Okay, but this is not obvious like this, so that's why I add an image to show how it works. Okay. And then how about performance? So we have this classification, CNN classification model. So we've trained it with 32 minutes of real data, 32 minutes of this diffusion model, conditional diffusion synthesized data, and then we have 128 minutes of generated synthetic data. So you can see these are the confusion matrix for 6 classes of activities. So the improvement, so you can see this can be much higher than real data, the limited amount of real data, the accuracy. And then again, we keep on increasing the amount of generated data. This dark line, black line, that is the 32 minutes as model trained by 32 minutes of real data, and keep on increasing it to the synthetic data from 32 to 64, 96, and 128. You can see the this is where F1 score that's like accuracy. So it's keep on improved. Okay, the more data you use, then you get better results. And the last part is that we use this stable diffusion. So that is a more recent technique used in Sora on creating those AI generated videos. Okay, so the idea is that we still do this kind of diffusion model, but we do this in the latent space. Okay, so we first wrap autoencoder. Okay, with the encoder will code the RFID data or Wi-Fi this wireless data into the latent space. Then in the latent space, we perform this kind of diffusion. It's called a stable diffusion. And then we use a decoder to decode these latent space features back to valid samples. So this is visually how similar the data can look like. This is real data for the walking activity, and this is latent diffusion, and this is a diffusion. You can see this is slightly better. Okay, and also the boxing activity. It's like the student is doing this kind of activity in front of the wireless device. Then you can see there's more activities in these rows corresponding to the upper part of the body with the tags attached to the arms and the shoulder. Then you see there's more variations here, and the lower part of the body, then less variations. So how about this matrix? So we have a synthetic data generated by this stable diffusion. Then we have real data. So we compute this matrix, compare them. So for diversity score, you can see now similarly as the GAN case. So these are very good. Okay. So this is the GAN model. This is the diffusion model. This is the stable diffusion model. This is real data. You can see they're about the same range. And then about this RFID score, so that is we compare the distribution of a synthetic data set with that of the real data set. So basically the lower means the distributions are more closer to each other. So you can see the GAN model, then the score is about larger. Okay, we have seen this before. Okay. Yeah, here you see the GAN model that give you larger RFID scores. But for this diffusion model and the stable diffusion model, they are more closer, about the same kind of level, maybe, especially the stable diffusion model, they're about the same level as the distribution of the real data. Okay, so this is really good. Then we use the synthetic data train, this is a classification model, and here are the confusion matrix. Then this one is trained by 32 minutes of real data. This is a model trained by 16 minutes of this stable diffusion synthetic data. And this is the confusion matrix for the model trained by 64 minutes of stable diffusion model. You can see the accuracy, okay, is 91%. That is a improved over this 83%. So that means if you have enough synthetic data, which comes at no cost, you can even your model can perform better by that trained by a limited amount of real data. So again, So we show this improvement from this the black line is 32 minutes of real data, and the green line is 128 minutes of synthetic data. So you can see the performance can be greatly improved with using this AIGC approach. Okay, so then it also saves you a lot of efforts on collecting wireless data sets. Okay. So in conclusion, so we talk about this wireless data challenge. So we unlike image, computer vision, or natural language processing based applications, then you can easily collect a huge amount of data from the internet, for example. But wireless data, you have to collect it from a field with real devices operating. In many cases, you need to collect synchronized data. So you have multiple sensors, like a video camera and a wireless device. You want to synchronize them with the same time stamp. Okay, so then that takes a lot of efforts, and then if you change your channel, then the data set will be useless. If you change your environment, then yeah. So basically, I think there's this problem hinders the wider application of deep learning models in to address wireless problems. Okay, and also if you are doing suppose you want to design some new systems, deep learning empowered system for 6G, but you don't have 6G device. You don't have there's no standard, no product. And how do you collect the data set for 6G to design an algorithm technique for 6G? So it's a chicken and egg problem, right? So there's a lot of challenges here. But we can use many techniques. Like you can use deep reinforcement learning, for example, and you don't need a lot of data. You can just try, then based on the response, you keep on changing, improving your policy, whatever. Or you can use meta learning to improve the general reliability. And in some cases, we want to detect some rare events, okay, anomaly detection of rare events, like sleep apnea. You sleep for the whole night, but it only happens maybe in a few seconds. So this kind of data is very rare, very hard to collect. Then you can use a variational autoencoder. You train the autoencoder using normal data, which is very easy to collect. Then if the input is anomaly data, then you can see that the output will be very different than you can detect. Okay, and then you can use imputation and augmentation. But we found that this AIGC is probably the best approach we tried so far, and we test the field. We show it's feasible to do this, and to use this generative AI, these models to synthesize wireless data, and then you can use this train your model to get good performance. That give you better general reliability, and saves you tons of efforts in collecting those data. And so far, we found a stable diffusion give us the best performance. Yeah, so sorry, I was a little bit harsh so quick, but I think then that gives us a lot of time for questions.
Thank you, Dr. Mao. So we show lots of interesting application. Yeah, and also this for wireless data. So yeah, most of the time it needs a lot of effort. So and also it's very valuable. If we indeed can develop some this kind of technology to generate the data, synthetic data by itself, I think this will be a bigger contribution to the wireless community. Okay, so any questions?
Yeah. So when you generate the synthetic post,
yeah,
how do you make sure that the generated post is possible?
Oh, well, we used a tool. A tool called Blender. So that is like a open source tool. So people use this tool for making video games. So
Right, I know,
yeah.
but you know, like sometimes,
Yeah.
because I think Blender doesn't have a feature where it will stop you if your, let's say your arm over hyperextended.
Okay.
You know what I mean?
Yes,
So how
yes,
do you
yeah.
make sure that is,
So yeah, we'll do a sanity check of these activities. Yeah. So basically we use this Blender, we tell Blender what kind of activity we want to generate. Then we get the skeletons. Then we'll see if it's feasible. It's not bending your arm or whatever. Then this will be fed into the GAN model or diffusion model to translate this to wireless. So we do not claim any contribution on this Blender type of work because that has been done by computer vision people. But our contribution is more like how to translate this to useful wireless data sets. That has not been done yet. Yeah, that's right.
Other question?
Yeah.
Yeah, so besides the activity sensing, like the recognition, is there any other, like say, applications of wireless data-driven research?
Yeah, this is exactly as you said. I feel like this is more like a general technique. So when I talk to people, like there are people working on traffic, network traffic monitoring, a similar situation. It's very difficult to collect a lot of data, and some like security problems. So how do you, because the security attacks are very difficult to collect the real trace, right? So this could be used to like the diffusion model can be easily adapted to generate like a channel modeling. You want to model some channels. So this can be used for those applications as well. I think, yeah.
Other question?
Do you know the mmWave radar bandwidth?
It's if I remember, it's from 70.
77.
It's NIS made the way. Let me see. Yeah, it's it's 77.
Okay, that's the
That's the
range, range, right?
yeah, it's about several gig.
Several gigahertz bandwidth.
Yeah, wow, yeah. We just bought the device, so
it must be.
I think it's
I see.
many people. Initially, this was used for autonomous driving, so
Yeah, no, mmWave radar, right? You can do
Yeah.
imaging, right?
Yeah, then people start to use this for vital sign monitoring, like your heart rate, your respiration, and so we just bought this and use it.
How expensive?
It's not very expensive.
Not very-
So as you said, one question I have been thinking a lot is that how can we compete with industry as academia researchers? So we only have a few students who are new, who have final exams, homeworks. They're not like full-time researchers. And we probably have one GPU. We don't have a farm of GPUs. We don't have access to huge tons of data so then probably we can work on some smaller problems like this. So this is not big data, it's a small data. And it's but more special kind of problems requires more domain knowledge. Then the equipment more accessible. And also you don't need a huge amount of GPUs to train your model. But if we use the key technologies, the same technology like stable diffusion, that is used by Sora, but at much larger scale. But we still can make some contributions. That's my the way I found out. Yeah.
Other question? So also one question for regarding the deployment and the practicality. So it seems that when you synthesize the data, you still need to have the real data, even limited sample, right?
Yes.
In this case, for example, if I already generate synthetic data in this room. How can I apply to another room? So I still need to collect some real data.
Yeah, you can, it's a good question. We tried the GAN model and the diffusion model. So in the GAN, in the case of GAN, so if we just use purely synthetic data, the performance will not be as good as real data. But we need to use maybe a small amount of 10 minutes, 20 minutes of real data. You can use that to, it's like a fine tuning. So then we get a similar performance. But for stable diffusion, then we don't need the real data. We just use the synthetic data. So basically you can, if the environment is changed, probably you can, we haven't tried a different environment, but we tried different subjects. Unseen, a new subject, new skeleton, we can input to get you data. So that still works.
Yeah, but for different rooms, they have different layout and different objects.
Yes.
So if like you don't have this real data to guide the training,
Yes.
like just use the diffusion model, even it's powerful. Like how can it like generate the high quality synthetic data?
Yeah, so we haven't tried that yet with different environment, but we tried different subjects. Yeah, in the same environment, maybe a change in move our chair, then the door open, that works. But we haven't tried a complete different environment.
I see. Yeah, I ask this because I know there's an environment effect that has
Yeah.
bigger impact to the wireless signal.
Yeah.
Yeah, for the object you change it, but the environment keep stable. So I think this doesn't matter. But if environment change,
Yeah.
like the different layout, they will have different reflection. The signal will totally change it.
Yeah, we were thinking about there's a new advanced control net. So basically, you want to generate something, apple. So you tell that should be an apple in this region. So it will generate image with apple in that. So we are thinking like you can use something similar, but we're still working on. Yeah. So basically use some more guidelines in the diffusion process to guide it towards some special settings. Yeah. Okay.
So those, most of the application you're showing here is indoor applications.
Yes.
Do you feel like is indoor is easier than outdoor or?
It depends on the application. So, for example, for localization, although you have GPS, then
There's no need for
you
this,
don't need
right?
this.
Right.
Yeah. But for some activities, probably because many activities are in close range are indoors. So yeah, that's why.
That's why I'm trying to answer Shi's question, because
Yeah.
indoor, many cases probably it's relatively stabilized. For example, you design for this building, right? So,
Yes.
yeah, so we're still.
I think because here, not more is using the RF radio. So only indoor we have the strong intensive RF radio, but for the outdoor we don't have like a Wi-Fi signal is weak, and also we don't have mmWave radar. So that's why so. But I think it's a bigger application for the indoor. So like the tracking and also fault detection or some other things.
Yes.
Yeah.
Yeah, that's very useful. Any other question? Yeah, so I think that's all you students maybe have very good body health every day. They need to do a lot of exercise. Okay, so no question. Let's thanks Dr. Mao,